In the last video, we focused on how to draw the cyclic hemiacetal forms of sugars using Haworth projections. In this video, we are going to learn some terminology that allows us to describe in words specific features that we observe within Haworth projections. So go ahead and take a look at this chemistry language lesson. We're going to learn a few different ways to classify hemiacetal sugars. One of those ways that we can classify hemiacetal sugars is by the orientation of the hemi-acetyl hydroxy group. This is largely a review of the last video. So classify them by orientation of the hemi-acetyl hydroxy group. Where if the hemi-acetyl hydroxy group is oriented downward, we describe it as an alpha sugar. So it's an alpha sugar if the hemiacetyl OH group points down below the carbon atom of the ring that it's bonded to. In a beta sugar, instead, the OH group is oriented upward. And in any case where an open chain ring cyclizes, this hemiacetyl hydroxy group is the newly formed chiral center, and that newly formed chiral center will exist as a mixture of alpha and beta. So if we're looking specifically at a particular molecule and it has the OH group oriented downward at the hemiacetyl position, we describe the sugar as alpha. If the OH group at that hemiacetyl position is oriented upward, we describe it as beta. Let's look at an example of this. In our sugar structure that I've drawn on the right here, we would classify this molecule as an alpha sugar. The way that we do that is we take a look for the anomeric carbon. The anomeric carbon is the carbon that is the hemiacetal carbon. So that carbon that's part of a hydroxy group and part of an ether group, we call the anomeric carbon. We look at that orientation of the OH group there at that hemiacetal carbon, or the anomeric carbon as we can call it. If it's oriented downward, which it is, we describe the sugar as being an alpha sugar. So we would certainly describe this as being an alpha sugar. So that's one way we can go about classifying our molecules. Let's take a look at another route to classifying these molecules. That second way that we can go about classifying molecules, instead of referring to the positioning of the hemiacetyl hydroxy group, we could also certainly classify them as D versus L. This is another topic that we looked at in the last video, but definitely worth mentioning because this is one of the key hallmark features of sugars. The sugar will be a D sugar if the CH2OH group is oriented upward above the carbon that it's bonded to. It'll be an L sugar if the CH2OH group is below the carbon that it's bonded to in the Haworth projection. Taking a look over at the right, our CH2OH group here is going up above the carbon that it's bonded to, and therefore we would describe this as a D sugar. These sugars are the ones that are most commonly prepared in nature. There are some bacteria and other unusual organisms that are capable of creating the L configuration sugars, but D is definitely the more prototypical one, and so that is the D sugar in this case. All right, additional ways that we can go about classifying our sugar molecules include number 3 in our lineup here. We can classify them by the number of atoms that are present in the ring. So we classify by number of atoms in the ring, where the fancy term that we use to describe a 5-membered ring hemiacetal is Furanose. So Furanose refers to 5 atoms in the ring. That includes the oxygen atom. The way that I remember this is by thinking of the F in furan refers to 5. 5 starts with a letter F. Furanose starts with the letter F as well. 6 atoms in the ring is referred to as a pyranose. That OSE suffix is what clues us in that these are sugars. 6 atoms in the ring and the pyranose. I don't have a clever way to remember that one, unfortunately, but P for pyranose refers to 6 atoms in the ring by definition. And so if we're classifying the structure up here, we would definitely refer to this as a pyranose because of the fact that it is the hexagon sugar. It has 6 atoms in total in the ring. Now, very commonly, these terms fuse together when we are describing the structure of a particular molecule. So if we were describing this molecule in a compounded way to represent several of the different features that we see here, we would describe this molecule as a beta D pyranose. And oftentimes these terms are made even more specific by, if this were derived from glucose, we would call it beta D-glucopyranose, referring to the fact that the cyclic sugar is derived from glucose. It has the beta orientation of the hemiacetal group. It has D rotation of polarized light, and since we use the term pyranose, that refers to the fact that it has 6 carbon atoms. So what you need to be able to do with this information is, if you're given the structure of a cyclic molecule, you need to be able to classify that molecule based on using the different terminology here, or you need to be able to, in other words, apply this terminology wherever appropriate to describe a particular sugar molecule. These terms are important because if we're trying to discuss a sugar in words rather than having to look at a complete chemical structure each time, we need to know the language that we are speaking to do that. Now let's take a look at this example problem. What I've drawn is a cyclic form of ribose shown here, and we're going to classify this cyclic ribose based on criteria 1 through 3 above. Ribose is an important molecule because it is one of the components that make up nucleic acids or make up our genetic material, DNA. So taking a look at ribose, classifying it based on the 3 criteria above, let's start with number 1, orientation of the hemi-acetyl hydroxy group, or in other words, orientation of the anomeric carbon. We recognize the anomeric carbon here as this position right here. That will always be the case in the Haworth projection. The anomeric carbon goes right here in our template. This is where the ether and the hydroxy group reside, and we classify it as alpha or beta based on the orientation of that hydroxy group at that location. Since the hydroxy group orients downward, we refer to this as an alpha sugar. Now, going to criteria number 2, taking a look at this, what we will find is that in categorizing this as D versus L, what we do is we look at the orientation of the CH2OH group, and we go from there with the CH2OH group. So looking at the CH2OH group and deciding what to do from there, we will, looking at this position, CH2OH group is oriented up, and so we describe this as a D sugar. Then we come to the next position, and at this spot, we talk about whether the number of atoms in the ring is 5 or 6. The number is 5, so we refer to this and classify it as a pyranose. Now, plugging all these terms together, we could refer to this structure as a whole as alpha D, referring to the configuration of the anomeric carbon, followed by the configuration of the molecule as a whole as D, alpha D ribo, referring to the fact that it's derived from ribose, and then furanose to let the reader know that it is a 5-membered ring. So dissecting this, alpha gives us the configuration of the anomeric carbon, D tells us that the CH2OH group points upward, ribo indicates it's derived from ribose, and furanose indicates there are 5 atoms in the ring.